Okay, today I will talk about enhanced Apex model, which is called Apex Model Flow model. And I will spend a little time on what is mode flow, RT3D. Let me just turn off because and how the Apex mode flow model works. And then we will move on to practical exercise. For example, building a mode flow RT3D and linking them with existing Apex model. But before we talk about some backgrounds, and let's install the software first that we are going to use. And especially QGIS is big and takes time to download and install it. So while installing it, I will talk about more backgrounds and introductions. So let me turn off this mode, and I'm going to use my second computer. It doesn't have any software. And I believe you've received this link, which is Apex Modeflow GitHub. And and then let's use this GitHub. And first we need existing Apex model dataset. And this time we are going to use Animas River Watershed Apex model. So let's click and download it. It might ask you about whether you want to keep it or discard. Then click to keep it and open the file. It's in the download folder, but this time for this exercise, I'm going to put all the data into desktop. So I create the d03 folder and I will unzip it here. In the Apex mode data folders, you will see Animas Apex model inputs. This is once you have ArcApex complete, you will get the text in and out. And also you will have the ArcApex model shape files. And we have the river and subbasin, also the DM. Okay. So Apex mode needs the QGIS 3 first, and then we would test Apex mode with long-term versions from 3.10 and 3.22. So you can click this button to download the QGIS, and there are two standalone kind of the latest release, and this is kind of people testing it, but long-term release version is more stable. So download this, click it, and you will get downloaded. And because I already downloaded, and it will be in the downloads folders. And here's the QGIS 3.22, and then you can double click it. It might ask you whether you want to install this program for admin rights, with admin rights, or just me. And you can just check this one. And I suggest to you to install for just me. But it seems this QGIS should be installed in the C drive, and that you might need admin rights. But if you have already installed with IT Guy, then you don't have to reinstall this QGIS. So let me put my mean, okay, so it's installing, and I will get back to the presentation mode. Okay, so as we've learned about Apex model for 2 days and 2 days and a half, Apex is really flexible, and then it is used many fields and small-scale watersheds, and due to more robust crop growth routines and details in nutrient cycling and sediment transport among the other watershed model. And we've also experienced it is flexible enough so that user can customize their own Apex models. Then why do we need model flow here? With the case questions, a famous quote by George Box comes out: all models are wrong, but some are useful. But when we look at more sentence, he said, all models are approximations. However, the approximate nature of the model must always be borne in mind. And this approximation or assumptions can be interpreted as uncertainty in the perspective of the modeler. And these uncertainties that can come from characteristic of your study site, simply they can be your model structures or parameter range or observed data noise. So the purpose of the developing or integrating model is to predict the behavior of certain process in your modeling framework. So like George Box quote, every model has its own approximation, and that generates high uncertainty on your model outputs. Like the other semi-distributed model, Apex treats water table dynamics, groundwater flow, and groundwater surface water interaction in a lumped and steady-state manner. Due to this non-geologically located groundwater table, flow and groundwater surface and water interaction, a standalone Apex model can cause high uncertainty on your simulate hydrological responses, especially in the groundwater-dominated watershed. And this fact, this standalone model can be limited to simulating groundwater development and management scenarios. Likewise, a standalone mode flow model is limited to investigating management, climate effects on groundwater and groundwater surface water interactions, because mode flow does not simulate surface processes such as land-atmosphere interactions, infiltration and surface runoff, nutrient cycling and transport, and especially the impacts of the management practice on agriculture system. Thus, Dr. Brian Bailey from CSU, Colorado State University, and here the scientists in Texas A&M successfully coupled the Apex code with model flow and WT, and even with RT3D code. And we've tested the model code with 6 different watersheds in Colorado River Basin and 1 in the Central Texas area too. And all model performances we've seen showed improvement on simulate stream flow and groundwater table. Then one of the mode flow RT3D we've integrated with Apex. I will briefly introduce the cores of this model. Henry Darcy, French hydraulic engineers, worked on the design of the filter large enough to process the D-zone towns in France. and daily water requirements. By flowing water through this center pack, Darcy established that for any flow rates, the velocity of the flow was directly proportional to the difference in this manometric height. From these experiments, he collected data on the length of the flume and the cross-sectional area of the flume. And the height difference here's head 1, head 2, and the flux of the water coming out of the flume, with or without these granular filtering materials in the flume. He then plotted the flux measurements normalized by the area versus the ratio of the height difference to the length of the flume. And what he found is there's a linear relationship, and the slope depends on this granular material he used in the flume. In a derivative of form, you might see that sometimes the negative sign. It is due to the fact that fluid flow downs, meaning negative, equals to the hydraulic gradient from high values to low values. In a 2D cross-sectional view, we can apply this simple Darcy's law in a subsurface system, so we can estimate this flow from H1 to H2, or the flow from subsurface to the river. So objective of the mode flow is to find this head at every location and for all times. And secondly, use this simulated head, and we can estimate the flow rate through the aquifer system and the flow rate to or from the aquifer, the river or stream system. So to apply this calculation to whole watersheds, we can divide this aquifer system into finite blocks, and we call it mode flow grids. And write the water balance for each grid. And the head here's we don't know yet, but by solving the system of the equation for H head, we can get the head, and finally we can compute flow rate through the aquifer system. And this is the simplified water balance equations for each grid. And as you know, mode flow is fully distributed 3D model, but I put here so X and Y direction only. And the source and sink, you can have recharge and pumping evapotranspirations. But in the Apex mode flow, Apex will take care of the recharge using simulated evaporations. Now we can replace these simple water equations with the partial differential equations. In general, this parameter during the parameter estimations, we use these hydraulic conductivities K and specific yield to match this head or the flow to target values. These partial difference equations and various algorithms and solvers written in Fortran language are compiled as a single executable, and then we call it mode flow model. We integrate mode flow entability version with Apex 15.0 version because mode flow entability version better satisfied the model complex nonlinear drawing and rewetting of the grid cell in an unconfined aquifer system. We can use various mode flow package, but they are mandatory package that we need to run mode flow model. So basic package contains initial water table head and the flags to define inactive or active cell of your mode flow grid. Also, we have the recharge package. Although the area lain by Apex model domains will receive the recharge from Apex, but the outside of the Apex domain, we can assign the recharge rate to the grid. River package contains three main information, such as initial river stages, riverbed conductance, and river bottom elevations. And these two, river conductance and river bottom elevation, also we call it riverbed thickness, will be important parameters to adjust groundwater contributions to stream flow. We also have a discretization package, and it contains the layer elevations and the mode flow simulations time step. And UPW takes of your parameters like hydroconductivity and specific gill, and WT is the solver package to control your flux tolerance and head tolerance. Here's RT3D, which is reactive transport in 3 dimensions, and it simulates the solid transport in subsurface area. This is developed by Pacific Northwest National Laboratory. And here are governing equations for nitrate and phosphorus. Changes in nitrate concentration equals to minus advection plus dispersions plus minus source and sink, and here's minus denitrifications. For phosphorus, we have the absorption coefficient in the left term for changes in phosphorus concentrations, and it is equal to minus advection plus dispersion plus minus the sink or source. I will not go over in details of this, but you can find the useful information in this link, and I will share these presentations later. It also uses finite difference method and same grid as mode flow, and it uses flow and source and sink information from mode flow simulations. Let's say we prepared or create all of the models, but to couple Apex with mode flow models, we need a spatial linking process. The figure in the left shows the spatial linkage between Apex sub-area and mode flow grid, and the Apex river network and mode flow river cells. The hydrologic fluxes passed between Apex and mode flow are depopulations from Apex sub-area to mode flow grid cell, and groundwater surface water exchange between mode flow river cells and Apex sub-area system. And to pass those simulated fluxes, we need the 3 linkages file and the 1 control file. And I will talk about more them when we do exercise.
Sungyu, there's a question on the chat
Yes.
asking the differences, what the differences are between MT3D and RT3D.
Okay, I cannot say they eventually same, but MT3D-MS or MT3D developed by USGS, and the RT3D, like I said, Pacific Northwest Laboratory developed, and they are using the same finite different method. But I think MT3D-MS has maintained by USGS, and they have a really nice tool called the Model Muse, and then you can develop the MT3DMS. And RT3DS is kind of more powerful because MT3D model, you need to have to run your mode flow model first so that you can have all of the simulate hydrological fluxes like a water table and the flow. Then you can run your MT3DMS, I guess. But the RT3D that we integrate with here is it is kind of daily time step simulation. So one day we run mode flow, and the same day we run the RT3D. So it's more like a dynamic linking. Almost the same. Almost the same, and has a little bit different format of your input file. Okay, let's go to where I was. Okay, so here's, and I think I finished this slide, and then this figure in the left shows the basic structure of the Apex mode flow modeling code. And the code begins by reading and storing input variable from Apex files, mode flow files, and linkage files. And the watershed simulation is run using daily timestamps. For each day, there are 5 steps that sequence will occur. So first, Apex simulates sub-area process in the land surface and soil zone. And the subroutines here, the code to pass Apex depolation to multi-flow grid and Apex sub-area stream stage to multi-flow river cell. Multi-flow simulates groundwater head for each grid cell and cell-to-cell flow rates, and also groundwater surface water exchange rates for each river cell. Multi-flow routines are called as the subroutines with the main Apex simulation routines. And the subroutines called to pass multi-flow groundwater surface exchange rates groundwater head to Apex sub-area. If the sub-area stream stage lower than the simulate groundwater head within the river cell, the water is removed from the aquifer and added to the stream, and vice versa. We can also check this process in an Apex sub-area scale and the multi-flow river cell scale. The last step is that Apex routes water through the watershed system network. And the water in the stream consists of the surface runoff, soil lateral flow, cube return flow from Apex routines, and groundwater discharges stream seepage from multi-flow routines. And the multi-flow code is compiled as a single executable. And we have added RT3D recently so that we can simulate nutrient transport with hydrologic fluxes in soil land surface and aquifer, and its interaction between groundwater and surface water. This slide shows a linking process in 3 different models. First, like I said, the Apex simulate all soil population potential ET, river stage, and irrigate irrigate water water required for irrigations, and the nitrate and phosphorus in populating water in stream water. Then multi-flow receive these informations and calculate water table height, groundwater interactions, groundwater flow, and source and sinks. Multi-flow passed this water table groundwater exchange to Apex again, and then now we have RT3D. RT3D received to simulate the nitrates, phosphorus from Apex side, flows, and source and sink from water flow side. Based on this RT3D, based on this information, RT3D can simulate the mass of nitrates and phosphorus and interactions with uh, Apex River network. Okay, so to provide the users with the standards and easy-to-use workflow for this enhanced Apex application evaluation, we developed a QGIS-based graphical user interface called Apex Mode. Now we are going to do hands-on exercise together. Okay, it's finished. Let's go ahead. Okay, let's go back to GitHub where I put it. Okay, this is not the one. So we download this input data sets. Now we have to then we installed this QGIS. And this time we are going to download Apex Mode installer. Let's download it. It might ask you this message. Yeah, I want to keep it. Show more, keep anyway. Then go back to download folders, and here's Apex Mode. It's executable. And double click it. Click the more info. This is this Apex Mode is going to be installed under your user account, so you don't need any admin rights. So run anyway, and it says Apex Mode 1.4.1. It's done. Because we installed QGIS. Let's do here QGIS. Okay. So we have a QGIS, and open up. Does any of you have a kind of latest version of the QGIS 3?
Hi, can you please repeat how QGIS is installed?
QGIS installed. Okay. Sure.
Thank you.
Okay. Here's the link, and install one of the version QGIS. It can be downloaded from this link, and then once you go there, you have three choice maybe. You can use this OSGO4W. You can use this two one, and this is the latest one, but it's not stable yet. And here's the long-term release, and you can just download this. And once you download, you can just click next, and check maybe to have desktop icons, something, and all will be finished.
So you started from the link you shared, right?
Yes. Here. Okay, did I close it? Yeah, here.
perfect. Thank you.
Okay. Any questions so far? Any other question? Okay, let's move on. All right. Once you have QGIS and Apex mode, you might not see this icon, but you can go this plugin menu and go to manage and install plugin. Click it, and you have the 6 different tabs, but once you click installed, there's Apex mode. Maybe unchecked it, then you can check it, then you will see this icon. Okay, let's click. And this is the interface of the Apex mode. I hope everybody can see this on your computer. And I've seen the issues the QGIS plugin or the Qt application, the graphical user interface has some kind of resolution issues. I hope you guys see this font size and this interface properly. Okay, let me move on. Okay, once you install, you will see this one. That's nice. Okay. So in the first tab, there are 2 options. Either user can create a new project or load existing project. And let's create a new project. You can click this button, and maybe I will put in the desktop in the day 3. It doesn't have to be, the same location, but I just want to make the simple path. Then you can name it the project. Maybe I usually do kind of prefix up your watershed name. So this is going to be Animus. So I will put any, and it's going to be exercise 1. So let me put exercise 01.
Sangyu,
Yes.
there are a few participants now who are still getting the QGIS installed.
Okay.
So they are not there yet to follow your lead on exercise yet.
Oh, that's the problem. Maybe, yeah, I'll wait because we have to install another one too, like a mini conda later. I think I just spent the 30 minutes, so I will cover the presentations I have. Okay. Actually, I finished the Apex mode flow presentations, but for the optimizations, let me put up. Okay, let's say we have complete Apex mode flow RT3D model. Then how are we going to proceed this integrate model optimizations? This model can be really highly parameterized and also be non-linear. And then you have to reconcile 2 different types of the parameters. They came from 2 different model, Apex and ModeFlow, and even RT3D. And this is the example of hydrological model structures, which is the source of uncertainty. So I put up like, the parameters in the different categories to explore this uncertainty. Excuse me. So as field parameters, you might have available water capacity of soil layer from apex. Also, runoff column number from apex, soil evaporation coefficient from apex. Here's a transmissibility from mode flow, hydraulic conductivity from mode flow, specific storage from mode flow, specific yield from mode flow. And also you will have to know there are lots of uncertainty, your boundary conditions. Boundary parameters can be your initial head boundary, also from your riverbed conductance and thickness. Also, it can be from your decision parameters, rainfall, recharge, evaporations. Luckily, we integrate Apex with mode flow so that recharge in the perspective of the mode flow, we reduced uncertainty from the recharge perspective, because in the mode flow, you have to input your the recharge directly, like to the grid, or pumping and injection rates. And we have another, um, the numerical algorithm uncertainty, because once we set your mode flow grid cell size, this is going to be another uncertainty that you can reduce. Like, final grid cell size is not always perfect. So you have to optimize your mode flow grid cell size, and there's lots of trade-off. Once you have a small grid and it creates more objects, then it will take more time to run your Apex mode flow simulations. Also temporal. Sometimes we do monthly simulation output, simulation optimizations. And that's kind of source of the uncertainty, but we put it this field parameters, boundary parameters, decision parameters, and numerical algorithms in different categories. Because of this, huge many parameters we have to assign or adjust it, we create this integrated model optimization workflow using Jupyter Notebook and Python scripts. We've been trying to, well, I'm still working on trying to this algorithm into this Apex mode, but it takes time. But usually, Python is going to take care of your um, Apex model simulation run here, let's say. Then as pre-processing, Python can create this three main input file for past parameter estimation tool. Here's the instruction, control, and template file. Then new parameters, Apex model can run, and post-processing, we have to extract all the simulation output. But usually Apex MF, this OBS contains your simulate water table. And here's RCH, which is channel simulation output from Apex. You can get the stream flow and post-processing for past, and using Python, we extracted this simulate value and sent it to past. In the past, to read this simulate value with observed value, then giving new parameters. to here's a PAM file, PAM 1501 dat, and also groundwater parameters can have the parameters in the river package or PBEL package. Even we can do a pilot point approach. I will cover during the exercise. Well, this is just one of the example, and you can, past has been developed so long, and then they improved that past utilities to explore like a global sensitivity analysis now, and then they do more like parallel processing also. So they used this one, the past plus they used these first order, second moment parameters for global sensitivity analysis, and they're using this executable. They can do that. Okay, I think we need to keep doing exercise. Do we need more time to QGIS installation complete?
Yeah, I need some more time, Shankar.
Okay.
Sorry, the internet
Well,
is very slow at home, and then it's taking forever to download the QGIS. It says 5 more minutes.
okay.
I had a quick question, Songyu. This is Thomas Harder.
Yes.
I was wondering if you could give some really quick while we wait. If you want to wait, some examples of like what scales is Apex mod being used at? How large can you go, and what's your typical number of layers in ModFlow and/or ModFlow grid cells, and what's how large can you construct Apex in terms of the number of, I guess, sub areas?
Well, that's really good question. Okay. First of all, I've been working on, there's another integrated model, strong mode flow. And then I've been working on more kind of 200,000 square kilometer watershed. And then I link with the mode flow grid. Grid size was 3 kilometer by 3 kilometers. And then you said how many layers usually we have to use. Well, it depends on the purpose of your research, I guess. So usually we should have one layer, obviously.
Yeah.
And it should be unconfined aquifer at the
Yeah,
first.
and I didn't mean to imply how many layers. I just wanted to kind of get a sense, like what's your lateral grid discretization, and you explained that very nicely just now. In how, what's the size of your total grid? And 200,000, that's a pretty good size. I mean, you can do a lot with that. That was actually, you answered my question on the ModFlow side. And then, so how large does Apex get when you do 200,000 square kilometers?
What do you mean? How many Apex get?
Like, I assume Apex has some form of discretization. I apologize. I wasn't at all the training sessions. But my take it is it's sub areas where you parameterize. And so how many of these sub areas would you then have in that 200,000 square kilometer model?
We'll have typically a few hundred sub areas, and try to keep it less 10,000 sub areas.
Okay, that's helpful. Thank you.
Yes, and then, like I said before, once you link Apex sub area with the mode flow, you will have the more objects, right? And then that will cause you to take more time. And then there's, and also you might need to consider the parameters you have to have for your model flow. So like I said, there are two ways, the journal approach and the pilot point approach. And the pilot point approach is really scalable, so that you might need like, well, for the Colorado River basins, I've been doing more the White River watershed. I've been using like a 200 parameters, usually 30 parameters that came from the apex, and then 170 or 150 parameters that comes from the pilot points.
Mhm.
And then once you have the pilot points, like 60 points, then that if you assign hydraulic conductivity and the specific yield and the specific points, you might have like a double it.
Yeah.
Okay.
And so can you, and you're still able to reasonably then calibrate a model that has, that's the size of what song you just mentioned?
Yes, that was doable, and then now it's more workable because um, in the past utilities have functionalities to perform the parallel processings. So once you have a more cores, like the 64 cores, and you are going to have a 124 threads, 64 at the 128 threads, then you can run parallel processing too, and it will really reduce your time.
And it's already programmed to do parallel processing?
In the framework,
Yeah.
framework that I'm going to cover my second sessions.
Thank you.
Yeah. Awesome. Okay, I think we can have 5-minute break. Then we can come back.
Thank you. If you don't mind, can you go back to one slide and then please explain again? Yeah, this
one.
Uh-huh.
Yes, I'm going to cover this on my second sessions.
Okay.
So usually when I do this primary estimations framework, I usually do like, I don't know, 1.5 hours Python and Jupyter notebook sessions, because I know everybody, I don't think everybody knows the Python language. So, and I'm trying to make all of the functions behind making Python package, and it's called Apex MF. It has not well documented. I'm trying to add in more informations, but using this, the Jupyter notebook just bring these functions and put the arguments, and all will just go over to the next session, next process. So, yeah.
Okay. Thank you. You're explaining very good. Yeah.
Thank you. Jihad, I think we can have 5-minute break and then start again.
Sure. Now is 10:46 in Pacific time, so we'll come back at 51.
Okay.
All right.
authenticating. But Ajahn Papa, I think for the first sessions, you don't need anything else. Okay, while we're taking break, maybe there's the second sessions, the material, and here's the another installations that we need. This is the mini conda, and then you have to download this mini conda. Once we go, well, let's not do this. Once you open this link, and there's a mini conda, and currently the Windows version is applicable, so you download this mini conda 3 Windows 64. I think you don't need admin rights for this. And I need to do install 2. So let me install this. I download already Miniconda here. And you can install it. Yeah, I think we can start here. Now it's
Thank you. There's a question on the
Yes.
chat window.
Yes, I already answered this question.
Okay, thank you.
So this Miniconda, let's start. I mean, yeah, this is another installations, and I think how many people we have here? Oh, 20. So once you download this Miniconda installer and then click it, and it will ask you about install for just me, all users. Let's do just me, which means this installer is going to install all of necessary file under your user account, and meaning you don't need admin rights. So I'm going to install it because I don't have it. And you can just go with the default. Okay. All right. While we're installing it, let's go back to QGIS. So if you open up the QGIS, please close, and then let's start the same side. So I'm going to open a QGIS. And let's open this Apex mode interface. And let's create a new project. And I'm going to put this new project here. And I will name, because this is Animus River Watershed, I will put any and exercise 1 and save it. And it says connected to database, right? And let's click OK. And let's go back to the folder where we specify the path to your project. So here's okay. Once you clicked OK for the database to connect to the database, and then you have to save it. This one. Let's just save it. Okay, where is it? desktop d3. Oh, okay. Okay, once we save it, there's a folder we are going to have like the same name, exact the same name as your QGIS file. In this QGIS Apex mode project folder, you will have 6 different folders. Apex MF exe is going to contain your all executable file. And this Apex mode is going to contain all of your models. And now you have mode flow, here's the Solidity. And once we import your Apex model, it's going to be in this side, in these folders. Here's the DB, which is database. It's going to take care of your all path, all of the file path. And here's exported files folders. Once you have simulation outputs, and then you can extract the sum of user preference simulation output, and all of the simulation output is going to install here, these folders. And here's the GIS folder, will store all vectors raster you create through Apex mode process. And we have also some scenario options like a dynamic drain, irrigations, but the irrigation is still under development. And if you use them, all generated file will be stored in these scenarios folders. Oh, okay, this is the QGIS file, I can see. Okay, now in the second tab, it will ask you to provide Apex model datasets, which are model itself, and it's going to be like a text in and out folders, and as a shapefile. So let's bring this text in and out, and that text in and out is in this dataset folders, and you can provide this one. So let's click this button, text in out button, and go back to this Animus Apex model folders. Double click it, and it's going to copy your original Apex input file. Because of these functions, you know.
Hi, Songyu. Sorry to interrupt. So actually, I think we just installed both Anaconda and QGIS, but I think I don't have the data downloaded yet. So I think we are lacking behind.
Yes, data, you can download this Apex mode link, and there's input link.
Oh, okay.
Then you can download this animals data set zip file and unzip it.
Okay, okay, perfect, perfect.
And I didn't, Miniconda installation is really good, and we are going to cover soon.
So that inputs, where do we have to save that file? And Animas dataset zip file.
Yes.
Do we also put it in the d3 folder on the desktop?
You can do it. I mean, it doesn't matter.
I mean, I was just wondering, like, if you have any paths, written into your codes or anything.
No, it's not.
Okay.
It's a user dependable path, and you can do it.
Okay.
And like I said, this functions is going to copy your original models or the data sets to Apex mode project. So you don't have to worry about any modification on your original data sets. Okay, I think I'm kind of cutting out. So let me close this. So it's done. We just copy Apex model. Now it's time to provide the sub-Bayesian shapefile and river shapefile. So river shapefile is in the Animus shapefile, and we have to choose the sub-Bayesian shapefile, and let's click this sub-Bayesian original shapefile. And you can see the QGIS canvas. Now we have animus subagent shapefile. It has 75 subareas. And this is shapefile is related to Apex, so shapefile is under this Apex tree. And also provide river. And river is now here. Okay, because we don't have, let's say we don't have the multi-flow model, but you can use your existing multi-flow model too. You can have like multiple layers, because the linking process is always going to be the first layer and the subbasin area. So we don't have multi-flow or multi-flow grid shapefile. So I'm going to choose option 3. And here's button to create a simple multi-flow model. And you will have new UI for the multi-flow model. Okay, using this one, you can have standalone multi-flow model too. Yes, the subagent shapefile is generated through the Apex. And you can create standalone multi-flow model by clicking this one and just go here or somewhere. Maybe I can put the day 1, and I will create a new folder for multi-flow model, and you can name it like any MF. And select the folders, and you have to name your multi-flow model. So I will give, because linking time depends on your number of the grid or the number of subbasins. So let me just give maybe 2 kilometer grid size. So I will put 2000. And the DEM, like we are going to use the DEM that we used for our Apex. So we are going to use the same DEM is in the animus shapefile folder, and let's bring open. Now we have here the DEM also that comes from the Apex. Okay, you can have different boundary between Apex boundary and multi-flow boundary, but I think the have the same boundary can have more, interactions, because let's say you have large multi-flow boundary and a small Apex model, and only the area intersected by Apex and multi-flow can pass their simulate result to each other. So for example, you have a large multi-flow, and small Apex subarea, then you will get small, that intersected area only get the recharge from it. The outside of the Apex boundary, you have to assign your recharge rate to your multi-flow rate. But I usually, give the 0 value for the recharge rate. I think I just answered your question, right? Okay, that's nice.
Yes, you did. Thanks.
Well, but there's like a pros and cons, and you can wait. I've been testing like a different spatial extent too, and then it's not really provide a huge uncertainty, but still, if you want to create Apex multi-flow model from very scratch, then it'll be better to have the same spatial extent.
Songyu,
Yes.
would it be possible for you to go a bit backwards and give the instruction again? Because I just missed the instruction because I was like getting the data and all. So
I think we are kind of short of time. Maybe in the lunch time, I can show you one more time then.
okay, no problem. Thank you.
This is really just a fast workflow. So this time I'm going to use the extent of the sub basin area shapefile. So which means I'm going to use this apex sub shapefile to create mode flow boundary. So I'm going to check it. Now we have mode flow boundary under the mode flow tree. And then now you can set up the mode flow grid size. You can do like, I don't know, 500. Then you will see the estimated number of the grid cell we are going to create. But this time, let's do 2000. And here's another options that you can add or subtract row and column. Because this QGIS algorithm to create like a fishnet shapefile doesn't take count of the number of a grid you are providing. They always care about like the spatial extent, and sometimes we might have like less one grid at the column or more row numbers than we expected. So you can use this one. I'm going to add one more row. And by doing this, you can have exact proper mode flow grid. I will show you this. So once we set up the size of mode flow grid, this is 1:1 ratio, and then let's click this create mode flow grid button. And now we are creating this mode flow grid. And we are extracting elevations from Apex DEM and then put all the value into this mode flow grid. Now you can see we have like a different ratio of the DEM for mode flow. The set unit, the mode flow is the unit is length. You have to use consistent units. Like for this one, this is the meter, I guess. And you have to keep using this meter units for all of your mode flow settings. And the time, I set the day because Apex mode flow run daily time step. Okay, so let me go back here. Yeah, we just create mode flow grid, and mode flow grid. Now once you open up, right click MF grid shapefile and open up the opportunity table, you will get the grid ID, and here's row number and column number, and here's elevation from mode flow. You might see the null because we are using we can only calculate activate cell. Okay. Okay, here's we have to assign hydraulic conductivity of the riverbed material, and this is a riverbed material. There's point. This is kind of default value from USGS, and we can give this. This is kind of parameters to adjust to your groundwater contributions and also riverbed thickness too. Because this is the meter, And point 1 is going to be your riverbed. Then let's create this modflow river cell based on this SWAT, the Apex River network. And let's create it. We just identify the river cell based on this Apex River network. And this MF river grid shapefile, you can open up the attribute table. Now you can have river stage, river conductance value, and river bottom elevation. And here's a layer number. And this information, this estimation that comes from this Apex river network. Once you open the river network attribute table, you can see here's the length and the width and the depth. And we are using this information too. Okay. And we are going to set the aquifer parameters. You can also provide a homogeneous value using raster file. Also, you can provide just a single homogeneous value. And for this purpose of this workshop, let's do just a single. This aquifer thickness mean is depth to the bottom layer is going to be 10 meters. Here's a hydraulic conductivity is going to be 1 meter per day. And then you can also choose the layer types. As a default, I put it unconfined, which is comfortable. And here's a specific storage value. Also, you can provide the raster, all of them, and the specific yield, single value 0.2. Specific yield is the unit. And here's initial hydraulic head value. This is going to be, because this is transient model, so you have to have the initial hydraulic head. And once the model is running, like warm-up period, the water head is going to be balanced. Here's a single value, depth to water table 2 meters below the land surface. You can also activate evapotranspirations that happened in the aquifer system. But let's not do this time. And here's well options. For example, pumping well or injection well. I've been testing it and still in progress. And once you set up all the things, let's go to the last buttons, write mode flow model. And this button is going to do all calculations and provide your mode flow inputs. Let's go to your mode flow folders, and now you see all the package we need. Here's a basic, discretizations, and name file return recharge will be 0 for this one, because we are getting the recharge from the Apex simulations. And here's the river package too, which is kind of important. And now you can see all the river cell, the river stage, river conductance, and river bottom elevations, row number, column numbers. And we using FlowPy package too. Okay, so once we finish to create mode flow model, you can just close this. It's done. And let's go back to main Apex mode interface. Now it's time to provide this mode flow model we just create to here. So click this button and go back to the folder and mode flow folder we just created, and double click it and select folders. And the mode flow model input has been copied to your Apex mode folders, which is this one, any exercise. And once we go to Apex model flow folders, you will see now you have all of the text in out Apex input file, yes, model flow input file. Because we provided this also the grid, you don't have to check anything. Also, we identify the rebuilders. So from using the Apex River network. So please check this one. You don't have to do anything then. Okay, if you want to get the simulate water table at a specific locations, you can provide the point shape file as the location of your monitoring well or their simulate monitoring well. So check this one, and I'm going to use observe the well point shapefile to get simulate water table at a specific locations. So I will show you here. Check it and browse it. And in the Animas shapefile folders, you will see MF OBS points. And I'll select it and open it, and it will just give you some idea, because sometimes your well is in not the first layer. You might have the well screen can be your second layer or third layer, and if you do, you have to go back to this MF OBS shapefile we just created and open a tribute table and change layer name, layer number, layer value. Okay, this is the point polygon that where we are going to get the simulate water table. Okay, this is done. Okay, this is kind of threshold settings on sub and grid size. Once you intersect the two different this object, you will have more objects. And sometimes the QGIS processing, it generates really small size of the objects. And from my experience, and the small sized objects doesn't affect your simulation output much, because that small object has the informations and that the apex passed deep operations to the mode flow as recharge. It doesn't make a huge impact. So you can filter it out using this one. I want to have not the DHLU, the flag divided the subbasin area bigger than size, something, this cubic meter per. But I'm not going to use this because we are using large size of the grid size this time. And here's another options to create RT3D model inputs. And also we just added this Solinity modules into this Apex ModeFlow RT3D. And now we are testing, and we are using soil data, but it's only available in the United States now. So we're testing this one, so you can just ignore this for this version. But we are going to do edit this function later. So let's create RT3D. Let's click it and open RT3D UI. And before we do it, let's save it just in case. And click open RT3D UI. And it's going to create RT3D grid shapefile in RT3D tree. And click OK. Now you have a new UI for RT3D model. and now we have RT3D grid. So again, you have to assign your RT3D model names, but you don't have to create another folder because this RT3D model is only workable with this Apex mode flow RT3D model. So I will name it any RT3D, just RT. And these are, RT3D property settings. And okay, I think, yes, you can also provide raster for porosity and initial concentration for nitrate and phosphorus. But this time, we are going to just examine the nitrate and phosphorus reaching from the apex to aquifer. So let's just do with a single value. Here's the initial concentrations for nitrate and phosphorus. And these absorptions, reaction parameters, I show you these from the governing equations. We're using just the linear absorptions, not the non-linear absorption parameters. So you can provide this one and this phosphorus PO4 partial coefficients. We got this value from the reference. And here's the first order ways of constant denitrifications. And these one can be used as the parameter for your model. Once you want, optimize your nitrate concentrations on your system. And here's aquifer dispersibility. And here's the bulk density and longitudinal dispersities. And also the ratio of the transfers to longitudinal dispersity and vertical. Here's effective molecular diffusion coefficients. We set to 0, but you can change. Usually we don't adjust this value. Okay, and then we also can provide observed point shapefile to simulate nitrate concentrations, phosphorus at a specific locations. But we are going to use the same point shapefile. This is the setting for the frequency of writing result, and this is only because we have lots of grid data format simulation output, and sometimes it takes more than 1 gigabytes, and sometimes it is hard to open it with the text editors because of memory issues or the limitations. And this means we are going to write a daily grid output, like a 365 days frequencies. So every 300, well, let's say 1 year, you will get the daily grid outputs. And let's write RT3D model. Now they creating you some of the grid or the edit grid, add the informations into this grid. And here's boundary informations. Because we select all of the single value, we didn't select raster homogeneous values. Now we have the RT3D. Here's it. RT3D file name, any RT advections, and basic transport package, and dispersions, and solver, reactive, and source async. But let's open this btn file, is most important. Now we write it based on our settings. So what they say we are going to use advections and dispersion package and source async and the reactive. we turn off the salt because this is under test now. We have two non-mobile, well, we are going to we say like compositions, but the species, we have two species, and type of writing output is going to be ASCII. We have two species. We are going to do mobile and immobile simulations, and we are using time as a day. And here's the concentration mass meter and the gram. Here's a porosity for each layers. Once you have more layers, and then they are going to write another rows. Okay, then here's the initial concentrations. Let's say we don't have any concentration this time in the aquifer, but we are going to get the recharge concentration from the apex simulations. And here's output times. We set like a 365 observation cell. We have it. Okay, I think it's okay. So we create RT3D. Now it's time to check your mode flow file. Let's check it. And it says checking mode flow input has been completed. Now it's time to start linking. So basically what they are doing is going to intersect your subbasin and the grid, and then do also intersect your apex ribbon network with mode flow grid cell. Okay, that's good. So here's Weaver and the grid polyline shapefile. We have it. So let's just turn off RT3D. And they are intersected sub-basin and the grid and Weaver and the grid Weaver network and the mode flow river cells. Okay, now simulation tabs has been activated. And this is simulation tab. This information just read by the apex con.dev file. And this is monthly, and the duration is 1,825 days. We are going to simulate the 2002 to 2006, but you can modify this now. Let's say apex con, I want to do like 10 years. Let's change the tab and then go back, and then we just extend your simulation period. But due to shortage of time, let's just apply for simulation period. Okay, for the configuration settings, because we create RT3D, and then we have observation cell, which is mode flow OBS. Let's just make sure we exported this. So check it. And this is groundwater delay parameters. You can do a single groundwater value, delay value for all subbasins. And this is going to be like a 3 days delay from the aquifer recharge, apex recharge to the aquifer. And or you can have like multiple one value for each subbasins. Once you do this one, you have to create another shapefile, and then in the shapefile you can modify this groundwater delayed value. And this is optional output for Apex mode flow simulations, and we are going to get all of them. Okay, let's create Apex MF link control file. This is last one. Let's create it. Now you can go back, and here's Apex MF link, and has all of the informations that from the configuration settings. So we flag it 1 for RT3D and flag 1 for reading mode flow observation cell. Yeah, it's time to run the model. That's the home not crashing. Yeah, you can see this is kind of daily simulations. You know, not like only Apex model. Apex model only shows this 1 year, but this is kind of daily simulations printouts. Okay, we done. Then we can change the tab now. This is the one thing we have to improve. But once you change your tab, because you have hydrology outputs and solar transport outputs, and those tab has been activated, you can plot your simulation outputs, like hydrograph for stream discharge, because this is monthly. And for Animas River watershed, we have the outlet and the subbasin 75. So I can choose the 75, and you can also, give all, different variable once you have different observed data. But this time we are going to do just this default one, water yield out. Then if we have observed the data, you can click this one, and I will show you how to create it. This is called channel day OBD file, and file extension is OBD. But this time we do monthly average stream flow. So select channel monthly OBD, and this file we have a different variable. This is stream flow discharge from subbasin 12, 57, 72, and 75. But this is the 75, so I will choose the 75 and then click the show. As a default, you will have just a point, the scatter plots for the observation data. But you can choose line also, then line works. And then you can have kind of objective functions, net uplift, R squared, P bias, etc. And if you need to skip some kind of warm-up period that you set, you can just select your simulation period. I want to skip 2 years for simulation output, then you can skip it, and it starts 2004 and have different objective function value. Okay, let's just go over this observed data file. Okay, here's a channel month OBD or channel day OBD. Observation data format is almost the same as the other model. Like you can open up this one in the text editors. The first column is the date, and from the second column you can have different location observed data, and in the time series you can put your observed data, the value, and then you can even, I don't know whether we have Excel here. Oh, we have it. Then you can sign. Okay, this is interesting. Yeah, you can open up this Excel file and you will get, you can adjust this value or, add more variable. Then save the Excel file as text delimited, tab delimited format. Then provide this prefix like CHA, then underscore. You can name it whatever you want, and then put your file extensions .ovd. You might need to delete txt once you saved this information from your Excel file. Let me show you this maybe in my computers. Yes, Excel. Okay. Okay. Here's the channel OBD, and I can just drag it. And now you can see here's the date and each location observe the value. And if you have a missing data, you can put -999, or you can just leave it as blank. Okay. Save it. So, and we have, let's say, site. This one file has really nice real format simulate output, but sometimes you want to have a like exact only the value in the time series in a specific subbase rich number. And here's exported button, and okay, and then I can click the export. Now it says channel is water ill monthly OBD sub 75 OBD text file was exported your exported files folders. So in your Apex mode project directory, there's exported files folders, and then you have this extracted simulate and with observed data file, and you can click it. Now you only have this 75 rich simulation output, and here's observed value and the time series. And then once you go to the bottom, you can also have the statistics. Same as the hydrograph for stream flow, you can have the same this. We don't have the mode flow OBD file for this model. Actually, we have like a small scale in this small scale Animus Apex model. We have it, but it's going to really different because we increased the grid size. But you can also see this daily water table or depth to water table. And here's once you click the daily and then choose the grid ID, and then you can click this one. And now you can see how you look at in the time series. Once you have observed the data, you can also provide it. Let's say this one too, hydraulic head. You can also check the depth to water table, not just water table. And the collect depth to water is going to give you, okay, depth to water 2 meters below. And then you can find some, about, I put up this one. then little, delay of the peak of the water flow, water table after we have high peak of the stream flow. So we can see some patterns, correlations between stream flow and water table. Okay, and then we can export the hydraulic head and the recharge to your mode flow grid shapefile. So let's do recharge, and then let's look at when we have really high peak flow, because usually in general you have a high precipitations, you can have a high recharge. So let's look at, okay, this is going to be May 2005 May, and you can click monthly average recharge, and you can choose this durations from first day to the end, but it's going to take time to export all of the grid data to the shapefile. So let me just show you what the actual workflow outputs. So here's AMF, MF recharge monthly dot out. You can click, this is the low data of your simulation outputs. And this is the grid data. You can have this one, and then, well, by manually you can copy some of the array at a specific time and then put the Excel and then make a raster, but it takes time. So let's do, once you use this Apex mode tool, you can easily export the simulate output. So that was 2000 May, maybe 2000 May, June. So I'm going to extract May month 2005 and June 2005 data into this, we just the shapefile we just created. Okay. Okay, let's export. Now they are adding it, those value into your shapefile. It's done. So we can use QGIS tool and make symbolized. And we are going to use graduate color and choose May 2005, and maybe go and no solid line, and I'm going to choose this one, a blues, and make like, I don't know, 50 classes, and I'm going to change the mode to natural break, and I don't want to see a zero value. Uncheck it and click OK, apply. And now you see we have a high recharge of on the upper area, and here's down little recharge. Okay. Then we can also see the groundwater surface water interactions. Right now, the animation functions I'm working on, but you can do also monthly groundwater surface water interactions. And well, we have might have high interactions on the May 2005, and I don't want to check the frame and click the show. Okay, this is kind of okay. Now you can see this red color indicates groundwater discharge to the stream, and here's blue, well, almost the same color. So let's do rainbow. Okay. And now you can see we have almost like groundwater discharge and little the groundwater seepage to the no, the stream water seepage to the aquifer. And also you can, download, export it to this specific date groundwater surface water interaction data. And go back to exported folders. Double click it, you will see here's X coordinate, Y coordinates, and your groundwater surface water interaction rate minus always indicate groundwater discharge to the stream, and plus positive value is stream water seepage to the aquifer. You can do, you can also, like we export this recharge, simulate the recharge for a specific range of the dates. You can also do this. Maybe I can export to this one for the last years to the shapefile. This save to the video is still testing. It's not activatable in these versions, but I'm going to put it soon. And we created this groundwater surface water monthly average shapefile. Once you go to attribute table, you will see now we have this January 2000 to December 2006 groundwater surface water interaction value. Water balance is really important. We are trying to put it, and you will get this result later soon. I think we have 10 minutes before lunch break. Maybe I can stop here, and right after you guys come back from the lunch, I can explain about this solid transport result too. So let's save this, and I will show you how to open your existing existing Apex mode project. So save this. You have to always save it so that you can have all the layer information and the path, and they are going to store into your database and the QGIS. So because we save it, you can close it, QGIS. Okay, thanks. Any questions so far? Okay, can they be specified? I think I don't know what the
Sandeep.
yes, what it means by lined.
Oh, I will explain. By the way, thank you. This has been great. I was wondering if you can also simulate canals, and Jayhawk answered my question that you can.
Okay.
And the follow-up question was, can they be lined, meaning can they have, concrete and not have direct exchange with the aquifer, or be non-lined?
I see. Yes. I don't know, Jia, can you explain or answer the question, please?
Yeah. It's not directly setting the model to simulate, concrete lined waterways versus just grass waterways. But when setting this irrigation and sources, we can set different amount of irrigation efficiency, and so that for those grass, waterways, as it will lose water through its conveyance, we can reduce the efficiency to lose some of the water during the irrigation processes.
Thanks.
This version of the Apex Mode R2 3D has dynamic drain linking process. So let's say you have a high water table, you can put the drain package on the mode flow. And once you have a high water table, the reach to your bottom elevation of your drain package, the water can go to your stream route. Then and with the way you can remove the water from your groundwater too.
So, Songyo, we have a few participants who was not able to were not able to follow the initial part of the hands-on. So,
Yeah.
While others are away for lunch, for those who need the first part of the demonstration, can you kind of go over again one more time?
Yes, it will take about just 10 minutes or 5 minutes.
Okay.
So,
Well, we'll take a lunch break officially until 1 p.m. Is that right? Yeah.
yes, I think
1 p.m.
Dr. Leon Mar has questions.
Yes. This morning I had something else, so I did not join most of the part. But back over to the Arc Apex, what the information like the DM or the polygon for the watershed are in the file in the folder already. If I do not have those file, just zoom to a place like in Colorado. How do I do that?
I mean, if you had the Arc Apex model created, then you have all those map layers available
Yes.
from the Arc Apex folder.
Even now you have it already, but what if I don't have it? I just want to go to a field to run Arc Apex. Can I zoom in to my experimental site and apply the model without I mean without like what you have are those polygons or those georeferences the watershed are those in your folder already? How do you create a watershed? What I mean.
This is the tool that the users supposed to have the existing.
What?
We assume the user who used this tool are supposed to have the existing Apex model.
You mean exact? No, not
Existing, yes.
You mean,
Yes,
watershed.
you have to already have your Apex model on the hand. Then you can provide this existing Apex existing Apex model to this tool so that it can help you to link existing Apex model with new mode flow or existing mode flow model.
So you mean I have to create the no? I thought for Arc Apex, you have watershed, right? You can mask the watershed, select which portion or which uh, outlet, or you can add those those watershed. Well, what I mean is that if I go to the field, like my field here, CPR, how can I use Arc Apex to draw a polygon and use the Apex model spatially?
You need to have your DEM to cover the study area.
Right. I
So-
can do that. How about the watershed?
Oh, once you have the DEM, that's a basic thing you need. Then the watershed delineation can help you get the channel, things like that. Then you need to have the land use, the soil, that's other GIS layer you have. But for watershed, you only need the DEM.
Okay, so when I have DEM, I can create a watershed. But what's the layers of once I have DEM, or the land use or soil type? Soil I can get should come automatically, right?
Yeah, I mean, that's the thing that we covered the first day of the workshop.
Yeah.
So, I mean, you don't have to use RKPax to be able to use Apex Mod, as far as you have, subarea boundaries and rich definitions already with you. Because this, mod flow is a specially distributed model, you need spatial boundaries to really contain mod flow grids and then connect mod flow and Apex.
Yeah.
So the easiest way is just you use our RKPax to create an Apex model, and then as about not byproduct, but as part of the output, you get what you need for mod flow integration.
Okay. So when use Arc Apex to create it, I need a DM, and also I need a layer of the management. What do you call it? The land use.
Yeah, you need the land use map, you need a soil map,
Right.
and then weather station location and time series data, daily weather data.
Okay. If I have a DM, will those information come automatically, or I have to?
No, DEM is a DEM, it's a raster data set, and you need to prepare for other map layers or inputs separately.
I know I have to provide DM, okay, to delineate the watershed. So
Okay.
if I have a DM, have georeferences.
Then you still need to download a land use map and soil map, and then weather data.
From what? From Arc Apex, from Arc.
Sources can be an RCS data gateway or USGS or other local government or public server where those land use maps are provided, soil maps are provided. Web soil survey can be the source for soil map.
Okay, so those are not automatically linked to Arc Apex.
ArcApex has basic map layers. I mean, property tables for an LCD, National Land Cover Data Set, and also Statsco Sergo soil map. But special map maps are not included.
Okay, okay. Yeah, I'm because one thing in my mind is we have like 8 stations in the Delta site or rangeland. I'm trying to say if the Arc Apex
Sure.
be used
Sure.
for those 8 sites.
Sure. Yep.
Okay.
We have another question, Floyd. Floyd, question?
Yeah, can you hear me?
Yes.
So, yeah, I have a question with 2 parts. Um, First of all, if I want to use Apex mod flow, So, do I have to necessarily do the calibration from Apex and Modflow first, or can I do can I evaluate the performance of the model just using the the integrated Apex Modflow?
That's a good question, and there's no one answer to that. The way that we have done in the past is that when we have an Apex model, then we actually did the sensitivity analysis and calibration for the Apex model itself, and then parameterize it as good as it can be. And then we did the mod flow integration, and then after that, we used the past that Songyu will continue in the afternoon for optimization. We use that tool to do one more round of actually multiple rounds of calibration and uncertainty analysis to the integrated model. So should we go for the coupled model calibration just straight ahead, or do the Apex model calibrate and then integrate and then do another round calibration? It's all it can be a part of your modeling strategy, and um, I don't know which way would suit you better. It is an open question. But basically, idea is that once we have Apex model all well parameterized, then it is a good model when integrated to the mod flow model. So when conducting a comprehensive optimization, once again with Apex and mod flow, we can hopefully expect that much less uncertainty that might happen. I mean, the uncertainty that might happen during optimizing much more number of parameters, looking at both Apex and mod flow at the same time. So we can actually keep the parameter spaces for all Apex parameters much narrower alongside mod flow parameters in the calibration.
Okay.
One thing I'd like to point out is once you integrate Apex with ModFlow in the framework, the Apex groundwater related parameter is going to be turned off. So if you already have the calibrate Apex model, you might have a chance to adjust to your groundwater parameters during the process. But once you move on to integration of the Apex with ModFlow, then we have a new groundwater parameter because we are going to turn off groundwater module in the Apex. Okay, let's take lunch break, and then if you want to create your Apex mod project, you can stay with me.
Well, it's another busy day. I can't believe this is already the third day of the workshop, and we are heading toward the last session today. One announcement I'd like to have before continuing the Apex mod flow, an exciting topic is that we're gonna send out to you all a survey form. It's a just a couple page of of questions that we'd like to learn from you in terms of how we can improve our workshop program by putting more focus on or less sparing less time, so we can kind of adjust our program to make it even more beneficial to the workshop participants. So hopefully you can spare a few minutes to fill up the survey form, answering questions, and then return to us, and then we will use it to make ourselves better. I mean, our program better for the next workshop. And then another thing is a certificate. So you all will get a certificate of the Apex workshop. We'll email you the PDF form of the certificate after the workshop. So it will be only next week. You will expect an email from us with the certificate with your name on it. So those are a couple announcements. Anything else? If not, then Sungyu, ready to continue? Well, Sungyu's been busy, and Sungyu and a few participants were busy all the way through the lunch break time, doing a lot of interactions of redoing the first part of the Apex Math Flow session, hands-on practices. So hopefully they are all where they are supposed to be to start the afternoon session, and then hopefully we all can carry on our exercise on to the next step of the math flow integration and RT3D simulation. I don't know, Sungyu, are you here? Come back?
Yes. Thank you. I will share my screen. So let's say we have, existing Apex. Excuse me. We have existing Apex mode project, and there's a way we can bring your existing Apex mode project we just create in the first sessions. So let's open up the QGIS and open up Apex mode. And here's the button, open existing projects. Once you saved in the previous project, you will get all of the data from this one. And click it, and now we have to choose the QGIS file that has your Apex mode project name. Mine was any XR01, and you can click it and open up. And it's connected to the database again, and you have a Apex mode UI and all the layers you've created. So saving is always important. Okay. Okay, for the visualization of the salt transport, there's lots of the room we have to improve also. So go back to salt transport, and this is showing you groundwater, surface water, solid exchange for each Apex sub area. So you can choose any other sub reach numbers, but I'm going to choose the sub 75. And then you can select the solid. It's nitrate and phosphorus. I will choose nitrates and show it. And then you might see a little noise, and then you getting, because this is interaction, you might have sometimes negative value. And this time negative value is going to losing the nutrients to the groundwater. And then you can choose the different time steps. And I want to have the monthly average nitrate groundwater surface water exchange. And click show. It's simple. We're getting more nitrate concentrations from the aquifer to your stream. And also you can do warm-up period control, and here's export buttons. You can also export this Apex Reef nitrate sub this monthly data to your Apex mode projects. And I put this project. And once you go to Apex Motor project folders, you will see here's exported files folder. And then now you can see we have this nitrate exchange data. And this is the rates. Okay, solid populations and concentration in the aquifer. This is the one I've been working on. This is not perfect. And then, but once you click it, this is the population from Apex. And this is going to create your new sub-basin file. And because this population comes from the Apex, but later on, we are going to make you have the grid scale population rate output. And like we did nitrates, there's nitrates. And you don't have to worry about this warning message that I need to fix it later. And then choose time steps. So once you choose this time step, it's going to say we have nitrates for collation monthly layer has been activated, edit your Apex MF result tree, and click OK. And then you can do like, I don't know, maybe 3 years. Because this is only 75 objects. So I can choose maybe 3 years simulation output. I want to put it this shapefile. So 3 years means 2004, 2004, January. And let's export. So every monthly average population is going to be in the store in your this shapefile. And once you open up the attribute table, you will get the extracted value from your simulate output file, and you will see all population rates, and you can even make colors to maybe do last year. No, let's do 2005 May. There was the time we have high peak of the stream flow. And I will get rid of this solid line. And because this is nitrate, maybe you can use this color ramp. And also 50 and change natural break. Okay, I think we don't have lots of nitrate. And uncheck the 0 value. Yeah, this is your nitrates concentrations. Here we can see maybe later animate plots this one to see kind of temporal variation of your nitrate concentrations, population rates. And also you can do phosphorus. And if I have a time, I will bring up the existing projects that has the salt module too. And also you can convert these vectors, any vectors map to the rasters or GIF. And because all of the gray, we have only RT3D nitrate population month, a shapefile that we can use to convert a vector file to the raster. So I will choose this. And then no data will be 0. And the mean value, let's say just, I don't know, 0.001. And let's give little colors in the minimum nitrate concentrations. And for the maximum, you don't have to decide it because it's going to read it, then make a maximum value. And for the maximum, high, red, dangerous colors, and then these durations, you know, we call it like a frame for seconds. It's a one frame that takes about 0.5 seconds. And then we can convert. Let's do a little, I don't know. And let's export, convert. And then you might see the rest file has been exported and or converted. You can see spatial temporal variation of your concentrations, and the form field was converted successfully. And then do you want to open the animated GIF file? You can open it. And here's the dates and then your spatial temporal variation of nitrate populations. And all the date, all the generate rasters, and the GIF is going to be in your Apex mode projector folders. I think the GIS folders, here's Apex MF shapefile, and it has the same name as your this nitrate population month. And once you go inside, you will have all the rasters. And here's last one in the GIF. So you can open up again and then use it as well. And also, you know, there's lots of the vector file you can use. Once you have this gray out of the list is going to be activated, and then you can choose it. Now we have an MF recharge before, so we can use it too. Okay, primary estimations I'm still working on, because this once you have a mode flow, your number of parameters is really scalable. So usually like commercial groundwater graphical user interface like groundwater Vista or Flex, GMS, they do have a past inside, past the program inside, and then they used pilot point approach. And I'm trying to do that too. So, but it depends on the funding availability, and I can spend more time on this. And also, while we waiting for this, for my second sessions, I made a optimization framework with Python script and Jupyter Note and pass to utilities, so we can move on to my second sessions. But before we do that, I think we have a little time. So let me bring up like the salt modules. But before we do it, this, once you go Apex mode folders, this out by extension means you have these outputs. So there's lots of the output you can explore and analyze this Apex mode flow model and RT3D model. I didn't show this. This is OBS we used computers, and you know we assigned some of the location that we need to have the simulate the nitrate concentrations, and it gives you all the locations and the value. nitrate concentration and phosphorus too. And also you will have, the grid base I showed you before. And then here's the groundwater surface interaction, phosphorus, and each cell you can have this phosphorus concentrations. Like I show you the groundwater exchange between like a groundwater discharge or groundwater seepage to the aquifer. And each day you can have these outputs. And what do we have here? Yeah, this apex mean, this is the sub-aging scale. And MF or mode flow means this is grid-based scale output. And here's RT3D, RT, and I think that's it. And I hope I can show you this salt data. Okay, fine. Before we do that, does anyone has questions about this Apex mode RT3D? I think I can just move on.
I just wanted to appreciate this was a great presentation. Thank you.
Oh, thank you. That's nice. Okay. Right. I might. No, not yet. Well, the paper is. I'm trying to write a publication now, but this salinity modules is now under the review. But I think once we create a video clip, that'll be enough. And after I publish my paper about this, then we'll think about making manual too. Okay. Apex. Give me a minute, please. Let me bring up the shot.
Singyu, while you are doing it, can you click on the hydrology tab on the screen?
Yes.
Thank you.
Okay. I think we have to move on. And I saved and close this project and share my another screen. This one. And I will bring up a project that we have salt module is in here. And this is Price River watersheds. And this is, once we have a salinity modules, you will get 8 different salt ions simulation outputs. Here's phosphorus, sulfate, calcium, magnesium, sodium, potassium, chloride, and carbonate, bicarbonate. And all this salt output can be visualized using this salt transport. And the one thing I want to show you is this is salt inputs. This is the same, almost the same as RT3D, the BTM file. And you will have a solubility product parameters for each, not each, these ions and initial concentrations, milligram per liters in the soil waters. And each column give you have like a sulfate concentration each subbasins. And here's initial salt to mineral fractions. This is the one we recently, with Dr. Ryan Bailey from Colorado State, we recently added in how to put the input, this Apex mode RT3D. So this is still kind of testing, but I hope it's going to be workable and soon. And then you can use this Apex mode to create this salt input and visualize the salt output. So if you have any, interest in this salinity analysis, please contact Dr. J. Hap-jung or me. And then if you want to see other, additional features of the salinities, then we can add more features while we enhancing this salinity analysis. And then here's a salt ion in the channel. Once we have these outputs, they're reading it because reading file is really big now, but each salt ions you can have, let's do monthly. You can analyze the mass or the concentration in each number, and this is price. I think the 69 is the outlet, and then you can let's say the potassiums and maybe skip 5 years and see potassium mass load on your stream as well. And also, I don't know, we have this. Yeah, this also, you can have this animation map or the vector maps, converting vectors to rasters. Okay, let's move on to the optimization sessions.